So my today's topic is again about test of significance, Z-test and T-test discussion. And first of all, I'm going to share this screen with you. Probably, I hope that you are able to see this screen where I'm showing you the uh, note on the part of the problem of the note which I uploaded in the Google Classroom yesterday. And I was supposed to take the class, but unfortunately, due to low network coverage, I couldn't take it. But I asked CR to inform all of you to go through my YouTube video so that at least you can see uh, that what I was teaching in my last class. And although I couldn't take the class yesterday, but yesterday's discussion was kind of vital because I discussed two important points regarding hypothesis testing. But anyways, I don't know whether you have gone through my video or not. I have decided today to discuss those 2 points first of all, and then I'm going to start my today's topic. And yesterday I actually solved the video which I uploaded in the YouTube. I was not satisfied with the video because let me share something with you. Uh, Actually, on each day, I actually have two classes, one with EC section A students and another with EC section B students. So after taking both the class, I record the class and I try to compare uh, which particular video is the most suited one, and then I actually upload the video. Yesterday I couldn't get this option at all. I couldn't take your class at all. So I was left with only one choice, to upload the video which I had. But later when I saw my own video, I said that in the beginning of the video, most of the time I stammered. It's because, and I repeated a particular statement various times, research paper kind of thing. So it happened because yesterday I was a little bit tensed because of this network connection. When I started taking the ECB class, then the network connection problem was actually there, and it actually gave me lots of trouble. Yesterday's entire day was a trouble for me with respect to this network connection. So my video was not up to the mark. So I am extremely sorry for uploading the low graded video in the YouTube. Anyways, since I had no other option and the video is a 42 minutes long, so therefore, and I also discussed some important parts. So I asked you to go through the video so that at least you can have your homework before you join my today's class. But one interesting thing also happened yesterday is that I have got the unlimited timing for Zoom, this particular Zoom class. Actually, suddenly when I was taking the ECB class, this particular message came on my screen that the Zoom is giving me unlimited access. I actually availed it, and I'm probably in today's class, after 40 minutes, no countdown will start. Zoom is actually providing in this COVID-19 situation the unlimited access for temporarily. Later they will withdraw it. Okay, so let's hope for the best. Yesterday I solved a problem whose Z value is given to be this. Okay, 2.192. Please, students, I'm requesting you, 15 students are there. Please write your roll numbers in the chat box. And those who have not finished writing, I'm saving the chat for the sake of the attendance. Okay, so in the last class, first problem, this was the this was the value of the Z statistic, 2.192. And I'm starting from this particular portion, because the important part which I'm about to tell you lies over here, okay, in this particular section. Now, you carefully observe that when we calculate the Z statistic, what happens? We get a value, And to draw the conclusion, we actually first of all calculate the p-value. Okay, and the p-value is calculated with the help of this particular formula: probability of modulus of capital Z greater than or equal to modulus of nu. Carefully listen to me. What is nu? Nu is 2.192. Okay, and this 2.192 value, this particular value sometimes can be positive and sometimes can be negative also. So since I'm using this particular form of the p-value, this particular formula of the p-value, so there is no provision of considering the negative value because I'm taking the absolute of this particular nu. So on the right hand side of the inequality, I'm writing mod of nu. On the left hand side, I'm also writing mod of z. And if I expand this particular, if I write explicitly this particular formula, we get this version has another form, which is twice probability of only z greater than or equal to mod of nu. So I have written over this. I've written this particular form over here. Okay. After that, you already know, I have discussed it several times, that we take the help of the statistical table. And this, on the basis of the value found in the statistical table, we calculate the p-value. Now, the statistical table which I shared with you, it's meant for, this table is meant for probability of z less than or equal to small x. Small x can be any value of z. So probability of z less than 2.192 is this particular value is 0.9857, which is obtained from the statistical table. And then I subtract this value from 1, because we know probability of complementary event is equal to 1 minus probability of the event multiplied by 2, which gives me the p-value. Now, one more thing which I must share with you is that you can calculate this also by yourself without taking help from the statistical table, because this particular expression is nothing but the integration from minus infinity to this point of the probability density function of the normal variate e to the power minus half z squared dz. So you can directly calculate this, not analytically but numerically, with the help of Simpson's 1/3 method or Wedel's method or trapezoidal's method. If you discuss this with your teacher who is teaching the numerical methods, he can tell you this in a more elaborate way. I'm not going to discuss because it's not under my jurisdiction. So it will unnecessarily kill the time. So I'm asking you to take the help of the statistical table, because whenever you do some kind of applied statistics on the system, you shouldn't waste time. And since the values are already there, then you can take the help of the values from the table. Now, the important point, once you get this p-value, then what happens? How to draw the conclusion? In one of my earlier notes, I told you that the definition of p-value, and if you are actually having the copies with you, copies in front of you, then you can write it once again for the sake of the understanding, that p-value is the smallest significance level at which the null hypothesis can be rejected. So suppose you have a normal curve and you have drawn the z-axis, and the z equal to 0 is the median, which is dividing the normal curve into two equal halves. So you can set a particular point on the z-axis, on the horizontal axis, and you can state that this point is my p-value. It means that if you draw a vertical line touching the normal curve on the right hand side, and another point which is at equal distance, just like with respect to the p-value. So suppose the p-value is the value of the p-value's value is p1. So you are considering p1 on the positive side and minus p1 on the negative side. So this means what? At this particular significance level, at this level of p1, your null hypothesis will be rejected. That is the definition of p-value. Any value greater than p1, you can consider any value greater than this point on the horizontal axis, at all of these points, the null hypothesis will be rejected. So you can say that this p-value is a kind of a bound which is minimum of all the bounds at which the null hypothesis will be rejected. So if you are going to select your level of significance in such a way so that it exceeds the p-value, obviously that null hypothesis will be rejected, because p-value is the smallest significance level at which the null hypothesis is rejected. Okay, try to visualize the thing which I'm telling you. So if my p-value is coming up to be 0.0286, and if I set my significance level at 0.05, then obviously the value 0.05 is greater than 0.02. And according to the definition of p-value, since p-value is the lowest significance level at which the null hypothesis is rejected, the hypothesis will be rejected at any level greater than this p-value. So the the hypothesis on the basis of which the z has been calculated over here, that will be rejected. But the discussion of the conclusion is not yet complete over here. I want to say more about this. Point number one, you may ask me this question: why are you selecting the p-value in such a way that it should be rejected? Okay, so try to consider the, sorry, why are you selecting your level of significance so that the null hypothesis gets rejected? You can ask me to try the to consider the level of significance in a smarter way so that I can accept the null hypothesis. Yes, I have done so. So here I have chosen the level of significance at 1%. And if the level of significance is at 1%, alpha equal to 0.01, then you see what is happening. That is the most interesting portion which I discussed in the last class. At alpha equal to 0.01, the value 0.01 is becoming lesser than the p-value. So if p-value is the lowest significance level, then if p-value is the lowest significance level at which the null hypothesis is rejected, any value lesser than that, at any value lesser than this, the null hypothesis will be accepted. You can treat p-value, because of this definition of p-value, you can treat it as a least upper bound. So at one level of significance, 0.05, the null hypothesis is getting rejected, but at another level of significance, 0.01, the null hypothesis is being accepted. And that is the most interesting portion in today's in this particular problem. Sometimes the problem remains the same, but sometimes we see that on the basis of the choice of the level of significance, it is getting rejected, and on the basis of the choice of the level of significance, it is getting accepted. So it may so happen also. Point number two, you can ask me, why are you selecting, if at 1% level of significance the null hypothesis is accepted, why are you showing this particular result, 5% level of significance at all? You avoid, we always in life, we always want acceptance. We actually are very much afraid of rejection. So we don't want to we don't want to reject things. We want to accept things. Okay, so you may ask me that if at one level of significance it is getting rejected, and at another level of significance it is getting accepted, you try to get hold of the acceptance region and forget about 5% level of significance. But I cannot do so. It is because what is 5% level of significance? What is level of significance? Level of significance is the probability of type 1 error. And 1% level of significance, it is also probability of type 1 error. So whenever you talk about 5%, the probability of type 1 error is 5%, then you have 95% confidence limit at your hand. And when the probability of type 1 error is 1%, you have 99% confidence limit at your hand. So we have to show to the people, we have to analyze the conclusion on the basis of both the confidence limits. Okay, we have to declare that actually what is the scenario. We cannot hide the statistics from the others. So if I do not say that at 5% level of significance it is getting rejected, then actually I'm hiding data, I'm hiding the conclusion from the general public, and which is not acceptable in statistics. So whatever you get, you have to, actually you have to analyze the conclusion. You have to draw the conclusion at all possible level of significance which is available. So what is happening nowadays? Different medicine, different companies are producing different vaccines, and they give you the percentage. So they actually are experimenting on the on subjects, and they are drawing conclusion out of this. But we do not have any idea at what level of significance they are drawing their conclusion. That has not been discussed in the newspaper, at least. But if you read the research paper, you can get it, the entire thing, the level of significance, etc., etc., etc. So if you ask me what should we do, then my reply would be, consider the conclusion at all possible level of significance. Okay, that is my verdict. Let us go to the problem number 2. In problem number 2, you see what is written. Actually, we had 10 volunteers on which we actually try to apply a medicine, and we want to see whether what is the medicinal effect on the volunteers. And for these 10 volunteers were chosen, and we treated those volunteers with vitamin C. Okay. How many volunteers have been chosen and applied? They were treated with vitamin C. 10 volunteers were there, and so 10 is less than 30, so the sample was small sample. There was another group which is called the control group, which had 12 volunteers in it. Those control group, those patients or those subjects which belong to the control group, they were actually given a placebo. What is placebo? Placebo is a kind of thing. It is not at all medicine. It is a kind of thing which has no actual effect, which has not the characteristic of the vaccine or the medicine. Placebo is just a kind of liquid, a mere liquid. But the patients do not know it. The participants in the control group, they do not know it, that they have been treated with the placebo. So after treating the 10 volunteers with actual medicine, and after treating the 12 volunteers with placebo, they were sent to the doctor. And the doctor is testing, without knowing actually, how long, what is the condition of the patients who have got the vitamin C and as well as the placebo behind the screen. But doctor has not been informed about that. After doing the experimentation, the experimenter have mixed up all these things, all the patients together, and they have he has sent the patients to the doctor. Okay, if the doctor is told that this is the patient who has got the placebo and that is the patient who has got the actual medicine, then the conclusion given by the doctor will be biased. So to avoid biasedness, nothing has been informed to the doctor. So in this particular problem, we actually applied the t statistics, and I did the calculation below. I'm not going into the details of the calculation, but here I'm going to say something about the null and alternative hypothesis. In the null hypothesis, what you see that I have considered the sample of 10 volunteers who were treated with the vitamin C with the variable capital X, and the 12 volunteers who have got the placebos actually with capital Y. This portion you carefully observe. Okay, carefully listen to me. This is very interesting portion. In the null hypothesis, I have written, instead of writing mu x equals to mu y. What do we mean by mu x equals to mu y? If I write mu x and mu y are same, mu represents mean. So mu x represents the mean of mean corresponding to the random variable x, and mu y represents the mean corresponding to the random variable y. So if when we write that mu x equals to mu y, that means there is no significant difference between the mean effects of the medicines on the patients. So I told you earlier that the equality sign should always be included in the null hypothesis, because the statistic which the statistical tool which you are using, this means I mean to say that this formula has been deduced under the null hypothesis. So if you do not include equality symbol over here, then you cannot use this in the formula. Actually, since I am writing mu x less than or equal to mu y, let me show you something. First of all, you will understand. In the above formula and the previous problem, you see the actual formula was like this. Z is equal to x bar minus y bar minus mu x minus mu y. Minus mu x minus mu y. See the next step. In the null hypothesis, we assume that mu x and mu y are same. So actually under the null hypothesis, this became vanished. So I only wrote x bar minus y bar, because if I say that mu x minus mu y, mu x is equal to mu y, so mu x minus mu y vanishes. So, but if I do not include the equality symbol, mu x equals to mu y in null hypothesis, we write it in alternative hypothesis, then if we go by the book, we shall not be able to write 0 over here, because the statistic is always based on the null hypothesis. Similar thing actually happened over here. So some mu x minus mu y was there. So because of our choice of the null hypothesis, that became vanished. My point is not that. My point is, why did I write less than or equal to mu x? Why didn't I write mu x equal to mu y? If I write mu x equal to mu y, then will there be any change in drawing the conclusion of the problem? The answer is no. You could have written the mu x equals to mu y. But I wrote it intentionally, and you have to understand and you have to learn this kind of thing where you will decide what to write in the null hypothesis. If I write mu x less than mu y, what does it mean? That the persons who are getting the medicine, their effect, the mean effect of the persons, mean effect of vitamin C is less than the mean effect of placebo. And here I am writing that mean effect of medicine is is more than mean effect of placebo. I am putting it in the alternative hypothesis. Can't we write mu x greater than or equal to mu y in the null hypothesis? Yes, we can do so, but then that will be a kind of biasness, I think. See, let us together analyze this. If I write mu x greater than or equal to mu y, what does it mean? I'm saying that mean effect of the medicine is more than the mean effect of the placebo. So there is, if null hypothesis gets accepted, then there are no provision of further experimentation on the medicine. That will be my ultimate declaration. Okay, the thing which is being done by the several vaccine production companies nowadays. Okay, but if we write that, okay, my mean effect of the medicine is lesser than this placebo, that means I am putting a kind of provision of further experimentation with the medicine, further development of the medicine, further upgradation of the medicine. So it is totally on the choice. It is based upon the manufacturer choice, how he wants to put the things in front of the general people. So in a clever way, he selects his null hypothesis and his alternative hypothesis. He can shuffle between the two if he wants. He has this provision of doing. But if you have to think that if you shuffle, then whether the honesty is compromised or not. So getting a particular problem and doing it and solving it and writing the conclusion, this is a technical approach. Whatever you are doing, you have to be well aware of this fact. And if you are not, then whatever happens, you will become responsible because you have drawn the conclusion. So statistics, I'm again repeating, and last couple of videos I have said several times that statistics is a manipulative subject. It gives you a kind of it helps you to manipulate things, but manipulation should be done in a clever way and in an honest way. It is not that you are doing it, you are randomly using it, and you are not thinking about the effect of the conclusion you have drawn on the situation. So ultimately, the thing after writing all these hypotheses, putting this null hypothesis and alternative hypothesis, I used the t-statistic formula, and I haven't shown the calculation in details because it is quite obvious. You can do it by yourself. Only thing I must say that this is the standard deviation part, and here you see in this part, this particular formula is kind of new to you. Here I have divided the quantity by n plus m minus 1 by n plus m minus 2. See, I told you that there are some problems with the network. Anyways, today's condition is much better than in previous day's condition. What I was saying is that n plus m minus 2, this thing is, n is the sample size of the first sample and m is the sample size of the second sample. And there is no hard and fast rule that which particular sample you are going to consider as the first and which were going to be considered as second. I can consider the persons with placebo as the first sample and person with vitamin C as the second sample. And since I am dividing this particular part by n plus m minus 1, n plus m minus 2, then your degrees of freedom, the number of independent variables in this case becomes n plus m minus 2, and you have to select the tabulated value of t at this degree of at this degree of freedom at 5% level of significance, and rest is same. I have seen whether my calculated mod t is greater than this tabulated t. If it is so, we are rejecting the null hypothesis. If it is not, then we are going to accept the null hypothesis. This is all about which I wanted to discuss in the last class. So let us now consider my today's actual topic which I wanted to discuss, and this is hypothesis testing concerning difference of population proportions. With this particular topic, I'm going to conclude module 5 of the syllabus. Okay, so regarding the syllabus, I'm telling later on. Let me first proceed with the this particular analysis of the situation. So here what we do, same thing, we select two samples of different size, capital Xi and capital Yj, one having the size small n and another having the size small m. And instead of getting the idea about mean of the two populations, we now have the idea of population proportions or population percentage satisfying certain characteristic. The population percentage satisfying certain characteristic corresponding to the X population is Px and corresponding to Y population is Py. We are interested in testing the hypothesis that the two population proportions are same. Actually, in this particular scenario, the test statistic is given by this particular formula. Carefully observe the formula, what I have written. Z is equal to small px minus small py minus capital Px minus capital Py divided by under square root Px qx by n plus Py qy by n. If capital Px is the population proportion of the X sample, then small px is the corresponding sample proportion of the X population. I shouldn't say X sample, X population. If capital Py is the population proportion of the Y population, then small py is the corresponding sample proportion of the Y population. Px, if Px is known, then Qx can easily be calculated because you know P equals to 1 minus Q. So in this particular case, Qx will be 1 minus Px. And if similarly, we can write Qy to be 1 minus Py. Small n is the sample size of the first sample, and small m is the sample size of the second sample. Again, there is no hard and fast rule. Which of the two samples you are going to consider as first and second. Now, if we want to test the hypothesis whether the two population proportions are equal or not, what we actually do, we write the hypothesis in this way. We write in the null hypothesis that yes, they are same. And in H1 we write no, they are not. So under the null hypothesis, under the consideration of the null hypothesis, this particular part vanishes. Px minus py becomes 0. And therefore your formula reduces to the following form. Z becomes px minus py by this. Now, if you consider that the two things are same, px and py are same, so obviously qx and qy will be same. So we can take the quantity px qx common, and I am writing it as px minus py divided by under square root sign px qx multiplied by 1 upon n plus 1 upon m. Okay. So this becomes my ultimate statistical formula on which will be applied to the current situation. Now, after this, we have to think about px. Now, px is the population proportion. I have said that px and py, these population proportions are same, but I do not know the value of the population proportions. So how can I write the value of the population proportion over here? To help in this regard, we try to use the pooled estimator. The pooled estimator is given by the following formula. What we do, we multiply x with y. X is the sample number of samples which characterize a particular thing. Y is the similar sample which characterize the other thing. So x plus y divided by total sample size n plus m, and this becomes, this x can be written as n into px, and this y can be written as m into py divided by n plus m. This is the pooled estimator which will help you to estimate the quantity capital Px. And once this capital Px is known, capital Qx can easily be identified. So I have written, subsequently I have modified my statistic as z equal to small px minus small py divided by under square root sign small pq, p into q, into 1 upon n plus 1 upon m. Here I have shown a problem. The problem says in criminal proceedings, a convicted defendant is sometimes sent to prison by the presiding judge and is sometimes not. A question has arisen in legal circles as to whether a judge's decision is affected by whether the defendant pleaded guilty or whether he or she pleaded innocent but was subsequently found guilty. The following data refer to individuals all having previous prison records convicted of second-degree robbery. 74 out of 142 who pleaded guilty went to prison. 61 out of 72 who pleaded not guilty went to prison. Do these data indicate that a convicted individual's chance of being sent to prison depends on whether she or he had pleaded guilty? So we have the proportions. We have the sample proportions with us. Sample size is also given. One sample size is 142 and another sample size is 72. Capital X is 74, capital Y is 61. But we do not have any idea about the population proportion. So if we go by the above rule, we will write the null hypothesis in the following way. And you already have the formula with you, so we can calculate small px by as the quantity fraction is 74 by 142, which is 0.5211, and small py is the fraction 61 by 772, which is 0.8472. Then you have to calculate the pooled estimator by the following formula, which is 0.6308. Okay. After all these, I'm going to substitute the thing in the z formula, and the value of z is coming out to be minus 4.67. So you know we have to consider the modulus of z. I have not shown over here the modulus part because I have written twice something. If I don't write 2, I have to write probability of mod z greater than or equal to mod nu. Keep this in mind. In the very first class of hypothesis testing, I have already told this. Now p value is calculated as this, And we can write this as 2 into 1 minus probability of z less than 4.67. Now you see, interesting portion is that if you see the statistical table, you will find that this thing will not be there. This part is missing. And there are reasons. If you see the statistical table, you will understand by yourself why it is missing. And since this value is missing, then we can ultimately write it as, if you say, you can say to me that, sir, if this value is missing, can I consider this value to be 0? The answer is no. If I consider this value to be 0, then what does 0 mean? 0 means the thing is impossible. So you are saying that this thing is impossible. Okay, but what will happen to the p-value? It will become, p-value is a kind of probability, isn't it? Why it is kind of probability? P-value, is it a probability? Yes, because p-value is a kind of level of significance, the smallest level of significance at which null hypothesis is rejected. And what is level of significance? Level of significance is the probability of type 1 error. So indeed, p-value is a probability. And if you write this as 0, the p-value, the probability will become 2, which is absurd. So since the data is missing from the chart, this particular data, so we shall write it approximately equal to 0. And since p-value is 0, so 0 becomes the lowest significance level at which the null hypothesis is rejected. So you select any significance level greater than this, 0.025, 0.05, 0.01, anything, 0.10. At all level of significance, the null hypothesis corresponding to this problem will be rejected. So my conclusion would be, any significance level you choose, the level of significance will be larger than 0. So we shall reject the null hypothesis. We can conclude that the decision of a judge with regard to whether a convicted defendant should be sent to prison is indeed affected by whether that defendant pleaded guilty or innocent. We cannot, however, conclude that pleading guilty is a good strategy for a defendant as far as avoiding prison is concerned. The reason we cannot is that a defendant who pleads innocent has a chance of being acquitted. Carefully read the conclusion. Once the class is finished and once you sit with this particular note, carefully see this particular conclusion which has been drawn. And I shall not ask you to do the calculations only. Think over it. Think over whether this conclusion, you are satisfied with the conclusion, or whether it is reflecting the current situation of the judiciary system. Okay, so thinking is very important, essential in statistics also. Since we do not have much time in our confined domain of the syllabus, the other things, other aspects of the statistics could not be discussed properly. Before a particular person starts experimentation, what we say, we say that he needs data, he collects data, but we never say that if he wants to collect data, then suppose I want to collect data for some of the experimentation of mine. A few days ago, probably I sent something, as far as I can remember, in the Google Classroom, and I asked you to fill up the form. I told that this was a part of University Amsterdam project. But before I before I go for the collection of the data, I must inform all the participants that I am collecting data for such and such reason. My actual objective may not be revealed, but I can give them a bird's eye view. Then once I get consent from those participants, then we collect the data and then we do our rest of the analysis. For the collection of data collection means sampling. You have to go for the appropriate sampling. You cannot just arbitrarily use any type of sampling which is available. Situations has to be properly understood. After analysis, when you give the conclusion, then also you have to think again and again over the conclusion. Before I conclude my today's class, I'm quickly overviewing this particular thing. This is the hypothesis testing concerning difference of population standard deviation. So that is another issue. If I do not have any idea about the population standard deviation, then we have two populations. We can, if I write the null hypothesis as sigma equal to sigma y, I'm testing this population standard equality of the two population standard deviation, we can take the help of this. Okay. And since population standard deviations are not known, we can estimate by the sample standard deviation. Okay, this is one aspect. Another aspect is I have given you a problem over here and I have left it for you to try it by yourself. These two samples are given. You have to test whether the difference between the means are significant. So you are going to apply the Z test for difference of mean here, and you are going to test the difference of standard deviation, that means the above one. Z test for Z formula for the above situation which I have just now told you. After drawing the conclusions, the interesting part is that if you see that your null hypothesis is getting rejected over here and getting accepted over here, or vice versa, your final conclusion is your null hypothesis will be rejected. Your null hypothesis can only be accepted if the complete hypothesis can only be accepted if the individual null hypotheses are accepted in both the cases. And this is the third situation where we tested the correlation coefficient. We can test also the correlation coefficient. You already know what correlation coefficient is. So we have chosen a data from somewhere, and the bivariate data, and the correlation coefficient has been, the population correlation coefficient have been assumed. How it is assumed? This is the way of assuming about population correlation coefficient. If the population correlation coefficient is denoted by rho, I am saying that the two variables which I am testing, they have in the population, they are uncorrelated. This is my this becomes my hypothesis, and it is universal. Then we choose n pairs of observations from the population, one for x, another for y, equal in size, and then we can apply t-test, where your R becomes the correlation coefficient between X and Y, the sample, the bivariate sample which you have chosen. And since I'm multiplying this by root over n minus 2, you can also consider that to be a division of under 1 minus 1 under square root 1 minus r square by this. So the degree of freedom in this particular case will be n minus 2. And we have to consider that this particular calculated value with the tabulated t value at n minus 2 degrees of freedom at certain level of significance. So when the calculated modulus of t is greater than tabulated t, your null hypothesis will be rejected, and if it is less than that, your null hypothesis is accepted. So this much for today. Before I conclude my today's session, I must tell you about the syllabus, condition of the syllabus. We are only left with only one topic. If you see the syllabus, it is chi-square test. So I am going to, in my last class, I am going to discuss the chi-square test and how to do the goodness of fit and independence of attribute. With that particular discussion, and also there is a thing which is called test of ratio of variances. So with these three things, we shall be able to complete our discussion of the syllabus of BSM 301. After that, in December, if we meet physically, I can go to your class, and I can, if the time permits and if the situation permits, we can discuss other problems also. And you continue your study. Don't leave everything for your last day's preparation, because mathematics is a kind of a language you have to be in practice with. And if you face any difficulties, then we can set any Zoom meeting to clarify your doubts. Okay. And since module 5 has been completed, so you start preparation of module 5 topics. And as I told you that I shall be sending a research paper which will go through, and on the basis of that, I will set questions and will answer, and that will be the way by which the CA3 examination will be taken. Everything will be told in details in the Google Classroom. Okay, so till then, goodbye and best of luck.